All right, so this video is going to be on the oxidation of alcohols. Okay, so we should know the oxidation reagents and the general process of oxidation of alkanes, right? So let's say we have methane, we oxidize that, we're adding an extra CO bond while removing a CH bond. That gives us an alcohol, and then we oxidize that, we can make an aldehyde. If we oxidize that aldehyde, we get a carboxylic acid. Okay, so we can definitely go further than this, but for this particular topic right now, oxidation of alcohols, we really want to just focus on the products, the aldehydes and the carboxylic acids. And then, of course, the fact that those come from the oxidation of an alcohol. Now, I'm going to point this out a few times throughout the video, but we really want to make sure that we're aware that these hydrogens right here in blue are essential for this process to kind of go forward. Okay, so in other words, if there's no hydrogens on there, then the alcohol is not going to get oxidized. So tertiary alcohols, you can't oxidize them. Okay, and you'll see why in the mechanism. We need those protons there. So let's take a look-see at a secondary alcohol. Really is what this is. We have oxidation of this, and we remove one CH and create another carbon-oxygen bond. So we have a ketone compound here, and then we're done. That oxidation process can no longer move forward, no matter how harsh our conditions. That's because there's no more H's. Okay, there's no more hydrogens. All right, now let's take a look, see at this guy right here. Let's say we have three. Well, oxidation, we don't have that proton present, so we can't actually move forward and nothing happens. So this tertiary alcohol in the presence of some oxidizing agents will just result in a tertiary alcohol and those oxidizing agents. Okay, so there's no hydrogens, and that's why this isn't going to move forward. Okay, so let's take a look at, or I guess a reminder, not a look. So remember, when we have a hydrogen and then we have a leaving group, anti to that, we can remove that proton and create the alkene product via an elimination, right? Well, this is pretty much what we're looking at for this chapter, is essentially just an elimination reaction to create a pi bond. But rather than that carbon-carbon double bond, we're creating a carbon-oxygen double bond. But in the end, it's still the same thing, right? So let me draw this as closely, as similar as possible. So we got two R groups on there. The oxygens doesn't have anything else on it. It's divalent, right? So the R groups, they could be hydrogen or they could be some carbon containing compound, so like an alkyl group. Either way, we do have that upper hydrogen and that lower leaving group, and we can deprotonate that hydrogen, creating that carbon-oxygen double bond, and then kicking that leaving group out to get a new carbonyl compound, whether it's an aldehyde or a ketone. Okay? Oh, right. Ryan Gosling says, interesting. Yeah. Do tell me more, please. I'm very intrigued. All right. Anyway, maybe you don't know who Ryan Gosling is, but best movie he ever made was, no, not The Notebook. It was Remember the Titans. Amazing movie. All right, so we've got CrO3, we've got our sodium or potassium dichromate. And then we also have PCC. So remember, these are the reagents that I introduced to you before. And so we do have these compounds with just tons of oxygens, right? And so these guys are obviously going to oxidize something. What are you going to do with all those oxygens, man? You're going to oxidize something. So that's PCC's structure right there, but we already knew that, right? So I'm going to highlight this one in blue because blue is cool and relaxed, and red is like pissed off and angry and just wants to ruin everything. So the upper oxidizing agents, those are really harsh. They're really harsh conditions inherently, but also they are used with sulfuric acid. So sulfuric acid and water as well. Sorry, sulfuric acid is a strong acid, right? So like you don't want to touch that. But PCC, is weak sauce, and it's used by itself. So there's no strong sulfuric acid. And so anytime you see PCC or those potassium dichromate or whatever, you're going to want to think about the strength of these. So remember, cool, calm, and collected PCC is chilling. It's blue. It doesn't have that harsh sulfuric acid, so it's weak. That means it's not gonna be as strong of an oxidizing agent. It's mild, while the chromium compounds above are very strong and harsh. Okay, and so what is the result of this? Let's say we have this secondary alcohol, this cyclohexanol, and we have this chromate, these chromates, sorry, as options. I'm putting M plus here just to kind of account for the potassium or the sodium dichromate. And then we can also throw PCC in there. Okay, so we're going to end up with this ketone compound. And that's just the general oxidation product of a secondary alcohol, right? And so in this case, PCC and the dichromate or the other chromate compounds, those are going to result in the same compound, which is a ketone. Okay, and here's a general mechanism. I'm going to use CrO3 to kind of explain this, but the general mechanism applies to all of them. Okay, so we have the oxygen, which is a Lewis base, and the chromium, it's a metal, right? So metals are generally just going to be Lewis acids, right? So they want to be attacked by Lewis bases, and that's what the lone pair on the oxygen does. It attacks the chromium. That kicks out the pi electron to the oxygen, and so what you end up with is this oxonium intermediate. It's a pretty much like a chromate ester, but they got a negative charge and a positive charge. So anytime you draw on a mechanism, you want to neutralize those charges. And so remember in previous chapters when we have like this scenario where we have a positive and a negative, we want to do a proton transfer. And a proton transfer is essentially deprotonating the oxygen to neutralize that, and then protonating the O minus on the other side, right? And it's going to be two steps. It's not like an intramolecular proton swap. It's going to be two steps. So we remove it, then we add it, okay? But we are also going to short form it and just write proton transfer and move on with our lives. Otherwise, these mechanisms can get even more tedious than they might already seem. So this is the intermediate product after that proton transfer. This is the chromate ester, and we have to imagine it as I kind of demonstrated before. Let's say we have a hydrogen sticking up, and then we have an oxygen with a leaving group on it. Well, what would you want to do? That leaving group is that chromium, that chromate ester, and the hydrogen is the hydrogen. So we remove that proton, create a carbon-oxygen double bond, and that leaving group pieces out. And so this again is very similar to the elimination reactions we've seen before, but now it's just creating a carbon-oxygen double bond instead of a carbon-carbon double bond. Okay. So that base is going to be water, removes that proton, creates that carbon-oxygen double bond, kicks out the chromium compound, and we get our ketone product, right? And then we also have this guy right here. And there you have it. So actually, sorry, I always forget to kick my lone pairs out on that chromium. So we kicked the lone pair out. We got that negative charge on that oxygen. Okay, and so that, in addition to, we got the ketone product, the chromium compound, and then we also have our acid forming in the end. Okay, but remember, that proton needed to be present in order to kind of move that elimination reaction forward, right? So if you don't have a proton there, then you can't do another oxidation. And so that's why secondary alcohols, you're just going to form a ketone. Okay, you're not going to form a carboxylic acid. But if you do have like an aldehyde, you do have that proton to kind of move forward to create the oxidation product, which is the carboxylic acid. The only time we're going to have two protons to remove is when we have a primary alcohol. Okay, so I'm drawing the two protons intentionally so that we are aware that they exist, but that's not always going to be drawn for you. So you just need to be aware. Primary alcohols, throwing some heat at it. We got chromium, we got our sulfuric acid and water. That's the harsh conditions, right? Now, what we're going to form first is an aldehyde, right? So we remove one CH, we create another CO bond, and we get the aldehyde. That's an intermediate. We can oxidize that further to get to our carboxylic acid by removing a CH bond and creating another CO bond. Bada bing, bada boom. Okay, so let's take a look-see at that mechanism. You're going to dislike this a lot, probably, because it's about to be all over the place. But it's the same thing twice. Okay, with just a little tiny little extra step in there on the second round. So oxygen attacks the chromium, Lewis acid, and then we end up with this intermediate here. We got all kinds of charges. What do we want to do when we have charges? We want to neutralize those charges before we move forward. So let's do a proton transfer, removing the neutralizing that oxonium, but then also creating that OH bond on the chromium. Okay, so now what do we have? We have a good leaving group, and we've got an acidic proton. Let's swoop on that proton, create that carbon-oxygen double bond, kick that leaving group out. Okay. Now, sorry, I threw my pi bond up too to create that negative charge on the oxygen. Trying to figure out where to draw this. So this creates an aldehyde, right? Now our aldehyde plus our chromium as well as our acid. So water removes a proton, that's going to create your H3O plus as well, right? And so let's go ahead and draw that because we need it. All right, so let's move this guy down here. So that way we can, this guy right here, move him down so we have more room for the mechanism. All right. Okay, so this carbonyl oxygen is basic, right? So it's going to get protonated in the presence of acid. And what you end up getting is this oxonium ion right here. Remember, that carbonyl carbon is already electrophilic, but now that it's next to a protonated oxygen, it's hella electrophilic, right? It's super positive. More susceptible to nucleophilic attack by water. Okay, so water attacks to neutralize that oxonium ion as well, creating another intermediate that does have a positive charge on an oxygen, but then we can just remove that proton real quick. And that gives us this thing right here. It's a carbon with two OHs on it, right? So it's like it's a geminal diol. And this is called a hydrate because we added water to that compound, to that carbonyl compound. And so this is a reactive intermediate, not super stable, but let's go ahead and draw it down here to move on with our mechanism. So if we kind of just ignore the OH, the additional OH on there, it looks like an alcohol with a proton, right? So what do we want to do? We want to start to oxidize that alcohol. So we attack the chromium, and then we end up with our charged intermediate, right? And then we can do, let me draw all these guys right here. So we got the OH there, and now we can neutralize the compound by doing a little proton transfer. Remember, this is a two-step process, deprotonation and then protonation. We're short forming it here for you. And we got our OH there and our hydrogen. Remember? Now this looks exactly like before, right? So we got that chromium leaving group, that acidic proton. Acidic proton gets swooped on to create a carbon-oxygen double bond, kicking out that leaving group. And lo and behold, what we got here? We got a carboxylic acid and the chromium compound as well as acid. But who cares about all the other stuff because we got our carboxylic acid. Yay! We got our compound. Bam, bam, bam. We did it. Done with organic chemistry. We're done. Woo. Okay. Anyway, sorry, I got too excited. We made a carboxylic acid, and that's really the mechanism. When you have a primary alcohol with, remember, the harsh reagents, CrO3, the potassium dichromate, sodium dichromate, whatever, sulfuric acid, strong, you're going to completely oxidize to the carboxylic acid. Okay, but PCC is weak sauce. Okay, so remember Eminem. What's up? All right, so we have this second primary alcohol. We got PCC. We don't have any added harsh acids. And so, again, it's just a mild oxidizing reagent. And so we mildly oxidize it to the aldehyde and we stop. PCC doesn't let it be a carboxylic acid. Do you remember the Eminem song? I don't know if you do. But he says, the FCC won't let me be or let me be me, so let me see. They tried to shut me down on MTV, but it feels so empty without me. Oh, thanks, Ryan. Appreciate that. Love you too. All right, so here goes. It may or may not help, but this is what I got for you. So PCC won't let me be, or let me be me, so use CrO3, because you can't be an acid without me. Hey, okay, bye. My daughter says hi.